Out there in the vast darkness of space, where light takes millions of years just to reach our eyes, lies one of the most colossal structures we've ever discovered, the Perseus Cluster. Imagine something so massive it contains thousands of galaxies, each with billions of stars, all bound together by gravity in a dance that's lasted billions of years. This isn't just another corner of the universe, it's a cosmic titan, a place where the laws of physics twist in ways we barely understand. And yet, despite all our telescopes, satellites, and supercomputers, this cluster holds secrets that defy explanation. 25 of them, to be exact, 25 mysteries lurking in the shadows of swirling galaxies and superheated gas, waiting to challenge everything we think we know about the cosmos. What if I told you some of these phenomena shouldn't even exist? Take the Perseus clusters, ghost particles, are strange, faint signals detected by our most sensitive instruments, whispers from the void that hint at forces we've never seen before. Or the way certain galaxies move as if tugged by invisible hands, defying the pull of gravity itself. These aren't just glitches in our data or gaps in our knowledge. They're cosmic puzzles, pieces of a grander picture we're only beginning to glimpse. And every time we think we've cracked one, another emerges, deeper and more baffling than the last. This is why the Perseus Cluster isn't just a scientific curiosity, it's a frontier. A place where the universe seems to wink at us, daring us to look closer, to question harder. Today, we're diving headfirst into those 25 unexplained phenomena, from eerie sound waves traveling through space to black holes behaving in ways that rewrite the rules. Whether you're a seasoned space enthusiast or someone who just loves a good mystery, this journey will leave you with one undeniable truth. The universe is far stranger, far more wondrous than we ever imagined. So buckle up, we're about to explore the unexplainable. Among all the cosmic mysteries within the Perseus Cluster, few are as perplexing as the case of the missing dark matter. Picture this dark matter, that invisible scaffolding thought to hold galaxies together, suddenly vanishing from entire regions of the cluster. It's like removing the foundation from a skyscraper and finding the building still standing, defying every law of physics we know. Scientists first noticed something was off when they studied the cluster's gravitational lensing effects, the way its immense mass bends light from distant galaxies behind it. The distortions didn't match expectations. Certain areas behaved as though a huge chunk of mass, specifically dark matter, simply wasn't there. But how do you detect something invisible in the first place? That's where X-ray observations came in. By mapping the superheated gas swirling between galaxies, researchers could calculate the total mass of the cluster. Subtract the visible matter, stars, gas, dust, and what's left should be dark matter. Except in these strange pockets, the numbers didn't add up. The gas was moving too fast, galaxies drifting apart in ways that made no sense without dark matter's gravitational glue. One theory suggests violent cosmic collisions might have ripped the dark matter away, like a tidal force scattering debris. Others wonder if we're seeing evidence of an entirely new behavior of dark matter, one that could upend decades of astrophysics. What makes this discovery so unsettling is how fundamental dark matter is to our cosmic models. It's supposed to be everywhere, the hidden framework shaping the universe. Finding voids where it's absent isn't just a gap in our data, it's a crack in the foundation of modern cosmology. Could our understanding of dark matter be flawed, or is the Perseus Cluster hiding an even deeper secret? Either way, these ghostly gaps remind us that the universe still holds cards it hasn't shown us yet. If the missing dark matter was the Perseus Cluster's silent phantom, then its ghostly radio halo is the literal voice crying out from the cosmic void, an invisible, swirling shroud of radio waves stretching millions of light years across space. This colossal structure doesn't just hum, it roars with synchrotron radiation, a type of emission produced when electrons spiral at nearly light speed through magnetic fields. But here's the twist. Nothing about this halo should be possible under normal conditions. The energy required to keep those electrons racing is staggering, like trying to power a city with a single battery, except the city is the size of a galaxy, and the battery ran out billions of years ago. So where does this relentless energy come from? One leading theory points to the cluster's violent past. Imagine two galaxies colliding, their black holes merging in a cataclysm so fierce it sends shockwaves rippling through the surrounding gas. These turbulent waves could act like cosmic accelerators, revving up particles to extreme speeds and igniting the halo's eerie glow. Observations of other clusters show similar halos often linked to ancient mergers, but Perseus' version is unusually bright and sprawling, as if something amplified the effect. Another idea suggests the cluster's own magnetic fields, twisted and stretched over eons, might be trapping and energizing particles in a self-sustaining feedback loop, a celestial generator we don't fully understand. Then there's the real head-scratcher: why some parts of the halo flicker unpredictably, pulsing in ways that defy models. It's like hearing a song where the tempo keeps changing, but no one's touching the dial. Some astrophysicists wonder if dark matter interactions, or even undiscovered particles, could be adding fuel to the fire. Others speculate that smaller, unseen collisions are stirring the pot, creating pockets of chaos in the magnetic soup. Every time we think we've pinned down an explanation, the halo throws another curveball, reminding us that the rules of particle physics might need rewriting when applied to such extreme environments. What makes this mystery so tantalizing is how it connects to the bigger picture. Radio halos like Perseus aren't just cosmic oddities, they're fossils of the universe's most energetic events. By decoding their secrets, we could uncover hidden chapters of galactic evolution or stumble upon entirely new physics. For now, though, the halo keeps its secrets, whispering across the radio spectrum in a language we're only beginning to decipher. And in that static, there's a lesson. Sometimes the universe doesn't just hide its mysteries in the dark. It broadcasts them loud and clear for anyone brave enough to listen. Deep within the Perseus Cluster's swirling maelstrom of superheated gas, where temperatures soar to millions of degrees, lies a cosmic contradiction. Razor-thin walls of icy coldness slicing through the inferno like ghostly scars. These cold fronts aren't just a slight dip in temperature, they're dramatic knife-edge boundaries where the gas plunges from blistering hot to freezing cold over a distance shorter than the span of our solar system. Picture opening an oven door and feeling a wave of Arctic air rush out instead of heat. That's the level of absurdity we're dealing with here. What makes these structures so baffling is how they stubbornly persist in an environment where they should vanish instantly. In a cluster like Perseus, where gas is constantly churned by gravitational forces and galaxy collisions, heat should diffuse evenly, smoothing out any sharp edges. Yet these cold fronts endure for billions of years, crisp and defined as if they were etched into the cosmos yesterday. It's like finding a perfectly preserved snowball in the middle of a volcano. The leading theory points to the cluster's chaotic past. When smaller galaxy groups plow into Perseus at speeds topping millions of miles per hour, their gas gets shredded and stretched into vast, swirling streams. Some researchers think these cold fronts are the remnants of those collisions, gigantic ribbons of cooler gas dragged along like cosmic seaweed in a tidal current. But simulations show these fronts should dissipate far quicker than what we observe. Something or someone is propping them up. That's where things get stranger. Some fronts aren't just cold, they're too cold, as if an invisible refrigerator were running in deep space. One hypothesis suggests weak magnetic fields, woven through the gas like invisible threads, might be insulating these structures, slowing their erosion. Others propose turbulence from hidden black hole activity could be reinforcing the fronts, like underwater currents preserving a layer of ice. But the most radical idea: these cold spots might be fingerprints of dark matter interactions, areas where the universe's most mysterious substance is subtly tweaking the laws of thermodynamics. The implications reach far beyond Perseus. If these fronts defy known physics, they could rewrite our playbook for how galaxy clusters evolve. Worse yet, they might be hiding evidence of forces we've never detected cosmic sleight of hand happening right under our telescopes. Every new observation deepens the mystery, proving that even in the most violent corners of space, nature still has tricks up its sleeve. Buried within the Perseus Cluster's sea of swirling X-ray light, where every galaxy and gas cloud paints the cosmic canvas with high-energy brushstrokes, there are pinpricks of radiation that refuse to be explained. These aren't the diffuse glow of superheated plasma or the telltale signatures of feeding black holes. They're sharp, pinpoint flashes like cosmic flashbulbs going off in the void, with no obvious source in visible light, radio waves, or infrared. Some shine steadily for years, while others flicker erratically, vanishing before astronomers can get a second look. And the most unsettling part, we've catalogued hundreds of them, yet they defy every classification we've got. What makes these X-ray phantoms so puzzling is their isolation. Normally, extreme cosmic objects announce themselves across multiple wavelengths. A supermassive black hole might blast jets visible in radio, while neutron stars often pulse with gamma rays. But these sources, silent everywhere except X-rays, as if they're deliberately hiding from our telescopes. One leading suspect is a population of rogue black hole stellar mass monsters ejected from their home galaxies during violent mergers, now drifting through intercluster space like cosmic nomads. Without stars to feed on, they'd be nearly invisible except for the occasional unlucky gas cloud straying too close, flaring up in X-rays as it's torn apart. Then there's the exotic star theory. Imagine a neutron star spinning so fast its magnetic field becomes tangled, creating sporadic X-ray bursts, or a white dwarf locked in a deadly dance with a hidden companion, siphoning material that detonates in unpredictable flashes. Some researchers even float the idea of quark stars, hypothetical objects denser than neutron stars, their very cores made of subatomic particles freed from normal matter's rules. Trouble is, no model perfectly explains why we'd see them only here in Perseus and not elsewhere in the universe, but the real curveball, a handful of these sources move. Slowly, almost imperceptibly, but enough to rule out typical stationary objects like pulsars. Could they be black holes propelled by ancient galactic collisions, or something stranger, cosmic debris from higher dimensions, as some fringe theories suggest? Every time we think we've narrowed it down, new data muddies the waters. Take Source 42, a particularly bright spot that dimmed by half over just 18 months, then abruptly reignited last year. Nothing in stellar evolution or black hole physics accounts for that timeline. The implications ripple far beyond cataloging oddities. If these are indeed rogue black holes, they'd be evidence of a hidden population lurking between galaxies, silently shaping the cluster's structure. If they're new stellar phenomena, textbooks will need rewriting. And if they're neither, well, that's the thrilling possibility that keeps astronomers scanning the static, because in the Perseus Cluster, even the smallest flicker might be the universe nudging us toward a revolution in physics. One thing's certain, when your mystery glows in X-rays but leaves no shadow, you're not just hunting an object, you're chasing a ghost. In the cosmic ballet of the Perseus Cluster, where galaxies whirl in an endless gravitational embrace, one performer has stepped wildly out of line, a supermassive black hole drifting untethered through the void like a lost titan. This isn't just any black hole. It tips the scales at hundreds of millions of solar masses, the kind of monster that should be anchored firmly at the heart of a galaxy. Yet here it is, streaking through intergalactic space at thousands of miles per second, leaving astronomers scratching their heads. How does something with the gravitational pull of a small universe get kicked out of its seat? The leading explanation points to a phenomenon called gravitational recoil. Think of it as the universe's ultimate kickback. When two galaxies merge, their central black holes spiral inward, locked in a deadly dance until they collide. If their merger isn't perfectly symmetrical, the resulting explosion of gravitational waves could rocket the newborn black hole in the opposite direction, like a cannon recoiling after firing. Simulations suggest these recoils can reach speeds over 3,000 miles per second, more than enough to escape a galaxy's grasp. But here's the catch: the black hole in Perseus isn't just wandering, it's dragging a faint trail of stars and gas behind it, a cosmic breadcrumb trail that shouldn't exist if it were purely a recoil victim. This ghostly tail implies something stranger. Perhaps the black hole was yanked out by an unseen force, or its host galaxy was torn apart in a collision so violent it left no visible wreckage. Then there's the trajectory problem. Unlike most runaway black holes, which should eventually slow and fall back into the cluster's gravitational well, this one is moving perpendicular to the expected path, as if steered by invisible hands. Some theorists wonder if dark matter filaments, those vast spiderweb-like structures thought to span the cosmos, could be tugging it off course. Others speculate it might be the remnant of a primordial black hole, born in the early universe's chaos before galaxies even formed, now surfacing like a relic from a forgotten age. But the most tantalizing possibility: we're witnessing a black hole mid-heist. In dense environments like Perseus, galaxies often steal stars and even smaller black holes from one another during close encounters. Could this rogue be the product of a botched theft, where one galaxy's gravity wrenched it away from another? If so, its path might trace a hidden history of galactic skirmishes, a cosmic crime scene we're only now deciphering. Whatever the truth, this wanderer challenges our assumptions about how black holes and galaxies evolved together. If monsters this size can go rogue, how many others lurk unseen in the darkness? And what happens when one barrels through a cloud of gas? Could it trigger star formation in its wake, or even birth new galaxies? For now, the questions outnumber the answers, but one thing's certain. In a universe where even the heaviest objects can be sent flying, nothing is ever truly anchored. At the heart of the Perseus Cluster, where gravity's grip is strongest, lies a cosmic anomaly so luminous it defies explanation: NGC 1275. This isn't just another galaxy. It's a raging powerhouse blazing with radio and X-ray emissions so intense they outshine entire galaxies 10 times its size. What makes this brilliance so baffling isn't just the sheer energy output, but the fact that it shouldn't be possible for a galaxy so ancient. Most central cluster galaxies like this are supposed to be quiet, their star-forming days long over, their supermassive black holes dozing. Yet NGC 1275 crackles with activity, like a dormant volcano suddenly spewing lava across the sky. Peering into its core reveals the first clue: an active galactic nucleus, a supermassive black hole devouring matter at a staggering rate. As gas spirals inward, friction heats it to millions of degrees, creating an X-ray maelstrom visible across the universe. But here's the catch: the energy radiating from the black hole's disk alone can't account for the galaxy's extreme brightness. Something else is at work, and that's where NGC 1275's most striking feature comes in. Vast, delicate filaments of star-forming gas, stretching tens of thousands of light-years like cosmic cobwebs. These structures, glowing eerie blue in Hubble images, shouldn't survive the harsh environment of a cluster core. The surrounding superheated plasma ought to shred them. Yet not only do they persist, they're breeding stars at a rate that dwarfs our own Milky Way. The mystery deepens when you ask how such ancient filaments even exist. One theory suggests they're remnants of a cooler gas reservoir, shielded by magnetic fields that act like cosmic umbrellas. Another proposes their fallout from a galactic collision, where turbulence and pressure sparked a delayed burst of star formation. But the most tantalizing idea ties back to the black hole itself. Jets of particles blasted outward at near light speed might be compressing surrounding gas, triggering star birth in their wake. It's a cosmic feedback loop. Black hole activity fuels star formation, which in time feeds more material back to the black hole, except the math doesn't quite add up. The energy required to sustain this cycle exceeds anything we've observed elsewhere, as if NGC 1275 is running on hidden reserves. Then there's the radio lobe paradox. The galaxy's colossal radio-emitting structures, stretching far beyond its visible boundaries, pulse unevenly, some regions dimming while others flare unpredictably. This isn't just random noise, it implies an engine misfiring, a black hole consuming material in fits and starts, yet there's no visible source for this sporadic fuel supply. No nearby galaxy is close enough to be stripped of gas, and the cluster's hot plasma shouldn't cool fast enough to feed the beast so efficiently. Unless, of course, we're missing an invisible player, perhaps dark matter interactions or a reservoir of cold gas lurking just beyond our detection. What makes NGC 1275 so critical to Unravel isn't just its defiance of expectations. It's a laboratory for the extremes of galaxy evolution, a place where the rules of star formation, black hole physics, and cluster dynamics collide. If we can decode why this galaxy burns so bright, we might unlock secrets about how the universe's largest structures grow, and why some celestial engines never seem to idle. For now, though, it remains a beacon of unanswered questions, shining a light on just how much we have left to learn. Stretching like ghostly tendrils through the searing plasma of the Perseus Cluster, the gas filaments near NGC 1275 are cosmic contradictions, delicate structures threading an environment that should vaporize them in an instant. These aren't just wispy clouds. Some span over 50,000 light-years, longer than the Milky Way is wide, yet they're thinner than a spider's silk in cosmic terms. Picture a sheet of tissue paper surviving inside a blast furnace, and you're close to grasping the absurdity of their existence. What keeps these threads intact in a region where temperatures hit 50 million degrees and galaxies collide like freight trains? The answer might rewrite how we understand chaos and order in the universe. Start with their bizarre anatomy. Hubble images reveal filaments glowing ethereal blue, their hydrogen gas ionized by some unseen energy source. They twist and curl like smoke frozen mid-dance, some braided into ropes, others fraying at the edges. But here's the first clue to their survival. Many align along invisible magnetic field lines, as if cosmic puppet strings are holding them together. Simulations suggest these fields, though a million times weaker than a fridge magnet, act like a scaffold, preventing the filaments from dissipating into the surrounding inferno. Yet that alone shouldn't be enough. Magnetic fields can guide gas, but they don't explain why these structures haven't been shredded by turbulence over billions of years, unless something is actively reinforcing them. Enter NGC 1275 supermassive black hole. Its jets screaming outward at nearly light speed might be the unseen sculptor. As these jets plow through the cluster's gas, they could create shock waves that compress and stretch material into filaments, like fingertips dragging through wet clay. But there's a catch. The black hole's activity is sporadic, flickering on and off over millennia, while the filaments appear stable. This has led to a wild alternative. What if the filaments are cosmic fossils, relics of ancient outbursts now maintained by residual energy? Imagine a ripple in a pond that never fades because the water itself has memory. Then there's the turbulence theory. The Perseus Cluster is a cauldron of violent motion, with galaxies and dark matter churning the gas like a spoon in broth. Normally, this should tear structures apart, but some astrophysicists argue the chaos might paradoxically preserve the filaments. Dense knots within them could act as anchors, swirling eddies protecting the threads from total disintegration. It's like a rope surviving a hurricane because its fibers are perpetually twisting, never letting the wind get a firm grip, but the real jaw-dropper. Some filaments are cooling. In a region where gas should be boiling hotter with time, certain threads are radiating heat away fast enough to condense into new stars, a process that shouldn't happen without some hidden coolant. Dark matter's gravity might be squeezing the gas, or perhaps undiscovered particles are siphoning off energy. Whatever the cause, these filaments aren't just survivors, they're cosmic alchemists turning the cluster's chaos into stellar nurseries. What makes this mystery so pivotal is its universality. Similar filaments appear in other clusters, suggesting they're not freak accidents but fundamental features of how the cosmos structures itself. If we crack how these threads endure, we might uncover a new law of astrophysics, one where even in the most hostile places, the universe finds a way to weave order from the storm. Until then, they float there, silent and defiant, taunting us with their impossible existence. Among the Perseus Cluster's countless galaxies, each ablaze with billions of stars, there's one that stands out precisely because it doesn't shine at all, a shadowy leviathan drifting silently through the cosmos. This isn't just a dim or distant galaxy, it's a pitch-black enigma, a structure the size of a major galaxy yet emitting no detectable light, no stars. No glowing gas, not even the faintest whisper of infrared heat. The only proof it exists, the way its gravity bends the light of galaxies behind it, a cosmic mirage revealing an invisible titan. How does something so massive, potentially weighing as much as the Milky Way, hide in plain sight? One possibility is that we're looking at a failed galaxy, a place where the gas needed to birth stars never condensed properly. Picture a vast cloud of hydrogen that drifted alone for billions of years, too diffused to collapse into stars, like a sky full of thunderheads that never produced rain. But there's a problem. Even these dark gas reservoirs should show some hint of stellar activity by now, unless something or someone kept snuffing out every spark. That's where dark matter comes in. If this object is a near-pure knot of dark matter, untouched by normal baryonic stuff, it could explain the absence of light. Simulations suggest such clumps should be rare, yet in Perseus they seem oddly common. Some researchers wonder if the cluster's violent environment stripped away any lingering gas, leaving behind a dark skeleton. Others propose an even stranger idea. These could be primordial dark matter blobs, relics from the universe's first second that avoided merging into larger structures. But the plot thickens. Recent observations hint that this dark galaxy might not be entirely barren. A few wispy strands of ionized gas spotted near its edges raise the possibility of an ancient collision, one that scattered its star-forming fuel like crumbs from a cosmic table. If confirmed, it'd mean we're witnessing a galactic murder scene with the culprit long gone. What makes this shadowy giant so important isn't just its eerie silence. If dark galaxies are real and prevalent, they could rewrite our understanding of how structures form in the universe. Current models assume dark matter and visible matter evolve together, but Perseus's phantom suggests they might sometimes go their separate ways. Every unanswered question about this object is a crack in the foundation of cosmology, a reminder that the universe's greatest secrets don't always announce themselves with light. Sometimes they lurk in the darkness, waiting for us to notice what isn't there. Deep in the heart of the Perseus Cluster, where galaxies crowd like spectators at a cosmic arena, astronomers have detected a strange glow, an unexplained flood of gamma rays with no obvious source. These aren't the faint flickers of distant pulsars or the expected signatures of dark matter collisions. This is a full-blown excess, a gamma-ray spotlight shining from the cluster's core with no one standing behind the switch. What's causing it? The answer could rewrite our understanding of particle physics or expose celestial phenomena we've never imagined. The mystery starts with the data. When telescopes like Fermi-LT map the cluster's high-energy emissions, they found gamma rays pouring out at levels that simply don't align with known astrophysical processes. Pulsars, those rapidly spinning neutron stars, emit gamma rays in predictable patterns. Dark matter annihilations, if they occur, should produce a different energy signature altogether. This excess is something else entirely, a steady hum of photons with no clear origin story. Some researchers initially brushed it off as background noise, a glitch in the data. But the signal persisted, sharpening into a puzzle that refused to be ignored. One radical theory points to actions, hypothetical particles long sought as dark matter candidates. If actions exist, they might convert into gamma rays when they encounter the cluster's tangled magnetic fields, like invisible ink revealing itself under blacklight. Another idea involves mirror matter, a shadowy twin to normal particles that could be hiding in plain sight, occasionally leaking energy into our universe as gamma radiation. These aren't just wild guesses, they're testable predictions. If actions or mirror particles are responsible, future detectors might catch their fingerprints in the energy spectrum. But the plot thickens when you consider the astrophysical alternatives. Could a population of hidden millisecond pulsars, too faint to spot individually, be pooling their gamma-ray emissions into this excess? Or is there a gargantuan black hole at the cluster's core, funneling particles into collisions so violent they spark gamma-ray bursts we've never modeled? The challenge is that Perseus's central black hole, while active, doesn't seem to be working hard enough to explain the signal, unless, of course, we're missing a key piece of the accretion physics, some hidden mechanism that turbocharges particle acceleration. The implications stretch far beyond Perseus. If this gamma-ray excess stems from new physics, it could be the thread that unravels dark matter's identity or reveals extra dimensions. If it's astrophysical, it might hint at black hole behaviors or stellar remnants we've never witnessed. For now, the glow remains a beacon of the unknown, a reminder that even our most advanced telescopes are peering through a keyhole, and the universe on the other side is stranger than we dreamed. What makes this enigma so thrilling is its duality. It could be a signpost to revolutionary science or a cosmic mirage, bending our assumptions without breaking them. Either way, one truth emerges. In the high-energy heart of the Perseus Cluster, the universe is sending us a message in a language we're still learning to speak. In the turbulent heart of the Perseus Cluster, where galaxies collide and gas burns hotter than the sun's core, there's a celestial rebellion underway, dozens of star clusters shining with the brilliance of youth, their blue light defying the odds. These aren't just ordinary groupings of stars, they're stellar newborns, some barely a few million years old, bursting into existence in a neighborhood where the harsh environment should have snuffed them out before they even ignited. It's like finding a nursery full of infants thriving in the middle of a battlefield. The puzzle begins with their location. These clusters huddle in regions where the intracluster gas is so hot and turbulent, it should prevent the cold, dense pockets required for star formation from ever taking shape. Picture trying to light a candle in a hurricane, except this hurricane has been raging for billions of years. Yet somehow, against all logic, these clusters have not only formed but done so recently, their pristine condition betraying no signs of the wear and tear expected in such a violent cosmos. So how did they cheat the odds? One radical theory suggests they're the product of galactic pile-ups. When two galaxies graze each other in a near miss, their gravitational tug-of-war can compress vast clouds of gas into knots dense enough to collapse into stars. In Perseus, where close encounters are common, this could explain why these clusters appear in the debris trails of larger galaxies, cosmic sparks struck from the friction of passing giants. But there's a twist. Some of these young clusters aren't just surviving, they're thriving in total isolation, far from any obvious parent galaxy. This has led to another tantalizing idea. The cluster's own turmoil might be the catalyst. Shock waves from ancient collisions could ripple through the gas, creating pockets of high pressure where star formation triggers like a chain reaction. Simulations show these waves might act like cosmic bellows, squeezing gas clouds until they ignite with stellar fire. The real stunner, though, is what these clusters imply about the universe's resilience. If stars can form in the most hostile environments imaginable, it challenges the long-held belief that galaxy clusters are stellar graveyards, places where the chaos stifles new birth. Instead, Perseus suggests the opposite. Violence might be a midwife, sculpting the conditions for rebirth amid the wreckage. Yet the mystery isn't just about how these clusters exist, but why some outshine others. A handful blaze with dozens of massive, short-lived stars, the kind that explode as supernova within a cosmic blink. Their presence hints at a perfect storm of conditions, gas so rich and compression so intense that stars form in overdrive like fireworks set off all at once. If true, it means Perseus isn't just breaking the rules, it's rewriting them, proving that even in the universe's most unforgiving corners, life, or at least starlight, finds a way. What makes these young clusters so revolutionary isn't just their defiance of expectations. They're a living laboratory for how stars might form in the earliest epochs of the universe, when chaos was the norm and tranquility was rare. If Perseus can birth stars today against all odds, maybe the ancient cosmos was far more fertile than we ever dared to dream, and that changes everything. The Perseus Cluster should be teeming with dwarf galaxies, tiny cosmic islands, each holding just a fraction of the stars found in giants like our Milky Way. Theory predicts thousands of them, swarming like minnows around whales in this galactic metropolis. Yet when astronomers count, the numbers fall shockingly short. Where did they go? This cosmic vanishing act isn't just a head-scratcher. It threatens to upend our understanding of how galaxies evolve in the densest corners of the universe. One possibility is as brutal as it is elegant. The cluster's own gravity tore them apart. Perseus is a gravitational meat grinder where tidal forces, the same phenomenon that creates ocean tides on Earth, can stretch and shred a dwarf galaxy like taffy. Picture a snowflake drifting into a volcano. As these fragile galaxies orbit the cluster's core, the pull from massive neighbors might strip away their stars and gas, scattering them into faint streams too dim to detect. Some researchers have spotted ghostly trails of stars in Perseus' outskirts, potential grave sites of dwarfs long dismantled. But if destruction were the whole story, we'd expect more visible wreckage. Instead, the dwarfs seem to have vanished nearly without a trace. That's led to another unsettling idea. Maybe they never existed in the first place. Cosmological models rely on dark matter halos, invisible cocoons of mass that should have attracted enough gas to birth countless dwarf galaxies early in the universe's history. If Perseus came up short, it could mean those halos were somehow starved of material, leaving them dark and empty. Or worse, our models might overestimate how readily small galaxies form, forcing us to rethink the recipe for cosmic structure itself. But here's where the plot thickens. Recent ultra-deep surveys have begun spotting ultra-faint dwarfs in Perseus galaxies, so dim they're practically transparent, with fewer stars than some globular clusters. These phantoms are so hard to detect, they've slipped past telescopes for decades, camouflaged against the cluster's glare. Could the missing dwarfs have been hiding in plain sight all along, their starlight stretched thin as gauze? It's possible, but the math still doesn't quite add up. Even accounting for these stealthy objects, Perseus remains suspiciously underpopulated. Then there's the wild card, heat. The cluster's superheated plasma might act like a cosmic blowtorch, evaporating the gas dwarfs need to form stars, leaving them dark and undetectable. Or perhaps collisions between galaxies in Perseus' chaotic core merged dwarfs into larger structures, erasing them from the census. Each theory has holes, but together they paint a portrait of a cluster that's far more ruthless and far stranger than we imagined. What makes this mystery so critical isn't just the missing dwarfs themselves. They're keystones in the arch of galaxy formation, the smallest links in the cosmic web. If we can't explain their absence, we might be missing something fundamental about how the universe builds its structures or how it tears them down. For now, Perseus keeps its secrets, reminding us that sometimes the most revealing clues aren't what we find, but what we can't. The galaxies of the Perseus Cluster aren't scattered randomly like crumbs on a table. They're arranged in eerie, sweeping patterns, as if some unseen hand brushed them into cosmic filaments stretching millions of light years. This isn't just a quirk of perspective, it's a fundamental anomaly called anisotropic distribution, where matter clumps along preferred axes instead of spreading evenly. Imagine shaking a box of glitter and watching it settle not in a haphazard spray, but in deliberate, radiating lines. That's the level of strangeness we're dealing with here. So why does this happen? One clue lies in the cluster's violent adolescence. When Perseus was forming billions of years ago, it didn't grow symmetrically. Smaller galaxy groups likely slammed into it from specific directions, like asteroids striking a planet's surface at shallow angles. These collisions could have sheared the incoming material into elongated streams, leaving behind the filamentary structures we see today. Simulations support this, showcasing how mergers can stretch galaxies into vast, stringy formations that persist for eons. But there's a catch. Some of these galactic filaments align with voids, vast, bubble-like empty regions bordering the cluster, as if the galaxies are huddling along the edges of invisible walls. That's where dark matter enters the picture. Cosmologists believe the universe's large-scale structure resembles a cosmic web, with galaxies threaded along dense dark matter filaments. If Perseus's anisotropy mirrors this web, it might mean the cluster is still feeding, siphoning galaxies from intergalactic highways flowing into it. Recent observations hint at this, showing dwarf galaxies streaming along specific paths toward the cluster's core like cosmic tributaries. But the real curveball, some filaments point toward regions with no known massive structures, suggesting we might be seeing the gravitational imprint of something colossal lurking beyond our current maps. Then there's the magnetic field puzzle. Perseus's intracluster gas is laced with magnetic fields trillions of times stronger than Earth's, and these fields aren't tangled randomly, they align with the galaxy filaments. Could magnetic forces have guided the distribution, shaping galaxies like iron filings around a magnet? It's possible, though critics argue gravity alone should dominate at such scales. Unless, of course, we're witnessing a rare case where magnetism and gravity dance in lockstep, a partnership no one predicted. What makes this anisotropy so mesmerizing isn't just its defiance of expectations. It's a living fossil, preserving clues about the cluster's growth and possibly the universe's skeleton. If these patterns trace the cosmic web, studying them could reveal how dark matter molds the cosmos. If they're relics of ancient collisions, they might rewrite the story of how clusters evolve. Either way, one thing's clear: in Perseus, even the void between galaxies has a story to tell. The Perseus Cluster isn't just a hub of galaxies, it's also a cosmic transmitter, sporadically blasting out bursts of radio energy so intense they outshine entire stars in a fraction of a second. These aren't your average radio pulses, they're fast radio bursts, or FRB, some of the most enigmatic signals in the universe. Detected as fleeting spikes in radio telescope data, these bursts pack more energy than the sun emits in days into mere milliseconds. But here's the catch: we still don't know if they're screaming from within Perseus itself or just playing a cosmic trick on us by appearing to come from its direction. The debate hinges on two possibilities, each more intriguing than the last. On one hand, Perseus could host magnetar neutron stars with magnetic fields so strong they twist spacetime itself. When these hypermagnetic monsters undergo starquakes or magnetic flare-ups, they might unleash FRBs like celestial distress signals, Supporting this theory, one magnetar in our own galaxy was caught producing an FRB-like burst in 2020, proving these objects can indeed scream across the electromagnetic spectrum. If Perseus has even one such magnetar lurking in its dense core, it could explain the bursts, but there's a twist. FRBs from Perseus show a peculiar trait. Their signals aren't scattered as much as expected when passing through the cluster's thick plasma. This suggests they might originate beyond Perseus, their light merely grazing the cluster on its way to Earth. If true, the bursts could be cosmic lighthouses from galaxies billions of light years farther out, their signals amplified by Perseus' gravity like a lens. It's a tantalizing scenario because FRBs from such distances could help map the universe's hidden matter if we could just pin down their origins. The plot thickens when you consider the timing. Some Perseus-associated FRBs repeat, firing off multiple bursts at irregular intervals, while others are one-off events. Repeaters tend to favor magnetar-like sources, but singular bursts might stem from cataclysmic collisions, neutron stars merging, black holes consuming stars, or even theoretical phenomena like cosmic strings snapping. Without more data, it's like trying to diagnose a thunderstorm from a single lightning strike. What makes this mystery so electrifying is its stakes. If the bursts are local to Perseus, they'd offer a front-row seat to extreme physics in action. If they're background signals, they become tools to probe the universe's large-scale structure. Either way, every millisecond of these cryptic transmissions is a clue, and Perseus, whether their source or just a bystander, holds the key to decoding them. Until then, the bursts remain cosmic Morse code, flashing messages we're still learning to read. At the heart of the Perseus Cluster, where temperatures soar past 50 million degrees, there's a cosmic contradiction unfolding, a phenomenon so counterintuitive it's called the cooling flow problem. Here's the puzzle. The superheated gas in the cluster's core should be cooling rapidly. As it radiates energy away in X-rays, the gas ought to condense like steam on a cold mirror, forming a steady flow of cooling material that feeds star formation and fuels the central galaxy. But when astronomers measure it, the gas remains stubbornly hot, as if someone left a cosmic furnace running in deep space. This isn't just a minor discrepancy, it's a full-blown crisis for our understanding of how galaxy clusters evolve. The first clue to this mystery lies in the cluster's colossal scale. Perseus' core contains enough gas to make billions of suns, all packed so densely that cooling should be inevitable. Yet somehow, the system has avoided this fate for billions of years. Enter the leading suspect, the supermassive black hole at the center of NGC 1275. This monstrous engine doesn't just lurk quietly. It periodically erupts in outbursts of energy, sending shockwaves through the surrounding gas like underwater explosions rippling through a pond. These outbursts, powered by the black hole's accretion disk, might be pumping just enough heat back into the system to counteract the cooling, a cosmic thermostat keeping the gas perpetually simmering. But the plot isn't that simple. While the black hole's activity can explain some of the heating, detailed observations show the energy doesn't always line up neatly with the cooling deficit. Some regions stay hotter than the models predict, while others cool faster than they should, creating a patchwork of temperatures that defies straightforward explanation. That's led scientists to propose wilder ideas. Perhaps turbulence from galaxy collisions is stirring the gas like a spoon in a mug of coffee, redistributing heat in unpredictable ways. Or maybe the cluster's magnetic fields, twisted into knots over eons, are trapping pockets of energy and preventing uniform cooling. Then there's the dark matter wild card. If certain theories are correct, dark matter particles might occasionally collide, releasing tiny bursts of energy that could subtly warm the gas. It's a long shot, but in a mystery this deep, even fringe ideas get a hearing. What makes the cooling flow problem so critical isn't just the challenge it poses for astrophysics, it's what it reveals about the delicate balance of cosmic ecosystems. Galaxy clusters aren't static, they're dynamic, self-regulating beasts where black holes, gas, and dark matter engage in a perpetual tug of war. Crack this puzzle, and we might finally understand how the universe's largest structures avoid either freezing solid or boiling away into chaos. For now, though, the gas in Perseus keeps its secret, hovering at temperatures that shouldn't be possible, as if laughing at our models from the heart of the inferno. Scattered like ghostly afterthoughts among the Perseus Cluster's glittering galaxies lies a population of cosmic oddballs, ultra-diffuse galaxies, or UDG. These aren't your average star cities, they're faint, sprawling enigmas, stretching as wide as the Milky Way but glowing with only 1% of its starlight. Picture a city the size of New York lit by nothing but a handful of street lamps. That's the level of eerie sparseness we're dealing with. How something so vast can emit so little light isn't just a puzzle. It's a direct challenge to everything we thought we knew about how galaxies form and survive in the universe's most brutal environments. The mystery starts with their sheer tenacity. Most galaxies entering a dense cluster like Perseus get torn apart by gravitational forces, their stars scattered into the void. Yet these UDGs persist, their delicate structures somehow withstanding the cosmic meat grinder. One theory suggests they're failed galaxies, places where dark matter halos formed as usual, but something went wrong during star formation. Maybe their gas was stripped away too early, or perhaps their chemistry lacked the heavy elements needed to ignite robust stellar nurseries. The result: a galaxy stuck in perpetual twilight, all framework and no spark. But there's a twist. Some of these ghostly giants show signs of brutal violence, tidal tails, and distorted shapes, hinting they were once normal galaxies, shredded over eons by Perseus' gravitational tides. Imagine a loaf of bread pulled apart until it's just wisps of dough. That's what cluster tides might do to a Milky Way-like spiral, leaving behind only a faint, bloated shadow. Supporting this, recent studies found UDGs near Perseus' core often lack dark matter, exactly what you'd expect if they'd been gutted by gravitational stripping. Yet the plot thickens when you look closer. A few UDGs, particularly those lingering on the cluster's outskirts, still cling to hefty dark matter halos, defying the stripping narrative. Even stranger, some host globular clusters, dense knots of ancient stars, at rates rivaling far brighter galaxies. How does something so diffuse anchor such sturdy stellar jewelry? It's like finding a cobweb strung with diamonds. What makes these galaxies so fascinating isn't just their defiance of categories. They might be cosmic chameleons, products of multiple origin stories. Some could be primordial failures, others shredded survivors. Their prevalence in Perseus hints that clusters serve as dark factories, transforming normal galaxies into these spectral versions through relentless harassment. Or perhaps they're teaching us that galaxy evolution has pathways we've never imagined, where size and brightness aren't always linked. One thing's certain: in a universe that loves extremes, ultra-diffuse galaxies are the ultimate paradox, proof that sometimes the faintest whispers carry the loudest questions. And Perseus, with its army of these phantoms, is the perfect place to listen. But the Perseus Cluster isn't just playing tricks with light and gravity. It's also a cosmic alchemist stirring its gas with a heavy hand. Here, astronomers have stumbled upon bizarre pockets where the chemistry of the universe itself seems skewed. In some regions, the gas is laced with iron, oxygen, and silicon, the ashes of dead stars, while other areas remain strangely pristine, as if untouched by stellar explosions for billions of years. These aren't minor variations, they're stark imbalances, like finding a desert beside an iron mine in the middle of an ocean, and they're tearing apart our assumptions about how elements spread through space. For decades, scientists assumed galaxy clusters were well-mixed cauldrons. Supernova and active galactic nuclei were thought to churn their metallic debris evenly, like cream stirred into coffee. But Perseus laughs at that simplicity. High-resolution X-ray maps reveal element concentrations that vary wildly over distances as short as a few thousand light-years. Take iron, traces of it should be everywhere, since massive stars have been seeding the cluster with this metal since the dawn of time. Yet some zones show 10 times less iron than their neighbors, as if an invisible barrier kept them separate. So what's breaking the mix? One clue lies in the cluster's turbulent history. When galaxies collide, their supernovae don't explode uniformly. Instead, they litter their surroundings with metal-rich bubbles like uneven splatters from a paintbrush. Perseus' violent merger events might have left these pockets stranded, their heavy elements trapped in magnetic eddies or too dense to diffuse. Another possibility points to the supermassive black hole at the cluster's core. Its jets could act like cosmic plows, carving cavities that isolate metal-rich gas from metal-poor regions, creating a patchwork of chemistry. Then there's the dark matter factor. If certain dark matter particles interact weakly with normal matter, they might gravitationally shepherd metal-rich gas into clumps, preventing smooth mixing. It's a fringe idea, but in a puzzle this stubborn, even radical theories get a seat at the table. What makes this metal mystery so critical is what it reveals about the universe's recycling program. These heavy elements are the building blocks of planets and life. If they don't spread evenly, some corners of the cosmos might be starved of the ingredients needed to forge Earth-like worlds, while others drown in stellar ashes. Perseus, with its chaotic chemistry, forces us to rethink how the universe distributes its raw materials. Maybe the cosmos isn't a careful bartender mixing cocktails, but a messy chef, leaving chunks of flavor unevenly scattered through the soup. And that changes everything, from how we model galaxy evolution to where we might someday find planets capable of brewing life. At the core of the Perseus Cluster, NGC 1275's supermassive black hole isn't just active. It's rhythmic, erupting in bursts of energy so powerful they carve bubbles into the surrounding gas, leaving behind X-ray cavities like cosmic fingerprints. These aren't random explosions, they're echoes of violence occurring every 10 to 100 million years, each outburst leaving a ghostly imprint that lingers for eons. It's as if the black hole is breathing, inhaling matter until it can't hold anymore, then exhaling jets of plasma with enough force to rearrange the cluster itself. The evidence lies in the shadows. When X-ray telescopes like Chandra peer into Perseus' heart, they don't just see hot gas, they spot vast spherical voids, some spanning 50,000 light-years where the plasma has been blasted away. These cavities glow faintly in radio waves, their edges lined with magnetic fields and relativistic particles like the afterglow of a cosmic grenade. But here's the twist, they're nested. Multiple generations of cavities overlap like Russian dolls, proving this isn't a one-time event. The black hole has been erupting in cycles for billions of years, each explosion slightly offset from the last, painting a spiral of destruction across the cluster's core. What fuels this eerie cadence? The leading theory revolves around a feedback loop of feast and famine. As gas spirals toward the black hole, it piles up in an accretion disk, heating to millions of degrees until the radiation pressure becomes unbearable. The disk then erupts, flinging material outward in jets that punch through the surrounding gas. But the outburst also clears the table, blasting away nearby fuel until the black hole starves and quiets down. Over time, gas creeps back inward, restarting the cycle. It's a cosmic pendulum swinging between gluttony and expulsion, yet the mystery deepens when you examine the timing. These outbursts aren't perfectly regular. Some cavities are closer together, others farther apart, as if something or someone is tweaking the black hole's rhythm. Could mergers with smaller galaxies be jostling the gas supply like tapping a ketchup bottle? Or is the black hole's own spin warping the accretion flow, creating hiccups in the cycle? Simulations suggest both might play a role, but the real answer might lie deeper. Some astronomers speculate that dark matter, swirling in an invisible halo around the black hole, could be subtly modulating the inflow of gas, turning a steady stream into a stuttering trickle. The repercussions ripple across the cluster. Each outburst shapes Perseus' evolution, heating the surrounding gas and stifling star formation like a gardener pruning a tree to control its growth. Without these eruptions, the cluster's core might have cooled into a stellar nursery long ago. Instead, the black hole's tantrums maintain a precarious balance, preventing the gas from collapsing while also stirring it into a turbulent soup. It's a self-regulating mechanism, one that might explain why massive clusters like Perseus haven't burned out over cosmic time. But the most tantalizing question remains, are we seeing a universal rule, or is NGC 1275's black hole an eccentric outlier? Other clusters show similar cavities, but none with such a clear, layered history. If this cyclical feedback proves common, it could rewrite our understanding of how black holes and galaxies co-evolve, a dance of destruction and renewal written in X-ray shadows. For now, though, the echoes keep coming, each one a reminder that even the universe's most violent engines have rhythm. The seething heart of the Perseus Cluster should be a cosmic whirlpool, a place where superheated gas churns violently, stirred by colliding galaxies and shockwaves from ancient black hole eruptions. Yet when astronomers point their most sophisticated instruments toward this maelstrom, they find something utterly unexpected: patches of eerie smoothness. Like spotting a perfectly still pond in the middle of a hurricane, these regions defy every prediction about how turbulence should behave in one of the universe's most chaotic environments. At the core of this mystery lies a fundamental disconnect between theory and observation. Galaxy clusters like Perseus are giant particle accelerators, where gravitational forces and high-speed mergers should whip gas into a froth of turbulent eddies spanning thousands of light-years. Computer simulations consistently show this turbulence persisting for billions of years, transferring energy from colossal collisions down to microscopic scales through cascading whirlpools of motion. But recent X-ray and radio observations paint a different picture: vast swaths where the gas moves with unsettling coherence, as if an invisible hand has smoothed out the chaos. So where does the turbulence go? One radical explanation suggests that magnetic fields woven through the cluster like an unseen spiderweb could be acting as cosmic shock absorbers. These fields, though individually weak, might collectively dampen turbulent motions by converting kinetic energy into magnetic waves, a process called Alfvén wave heating. It's akin to how a mattress absorbs the energy of a bouncing ball, slowing its motion without a sound. Supporting this idea, some of the smoothest regions align with areas where magnetic fields appear strongest, hinting at an invisible taming mechanism at work. Yet there's a competing school of thought arguing that our turbulence models themselves may be flawed. Most simulations treat intracluster gas as a simple fluid, ignoring subtle quantum effects or potential interactions with dark matter that could alter energy dissipation. Imagine trying to predict ocean waves while ignoring the effects of underwater topography. You'd miss critical details. Some theorists propose that at extreme temperatures and densities, plasma physics behaves in ways our equations don't yet capture, perhaps allowing energy to leak into particle interactions we can't observe directly. The most tantalizing clue comes from the cluster's history. Perseus has likely endured multiple major mergers over billions of years, each collision injecting fresh turbulence into the system. If the gas were truly as smooth as it appears, those ancient impacts should have left visible scars, wrinkles in the fabric of the plasma. Their absence suggests something is actively erasing disturbances far faster than standard physics allows. Could dark matter particles colliding with gas molecules be acting as microscopic breaks? Or are we witnessing the fingerprints of entirely new plasma states, where energy dissipates through mechanisms unknown to our textbooks? What makes this enigma so pivotal is its universal implications. turbulence isn't just a curiosity, it governs how clusters distribute heat, form stars, and even how they grow. If Perseus is hiding a secret about how cosmic storms quiet themselves, it could rewrite chapters of astrophysics from galaxy formation to the life cycles of the universe's largest structures. For now, the smooth patches remain, silent and enigmatic, challenging us to reconsider whether chaos always follows the rules we've written for it. If dark matter truly forms the invisible skeleton of the universe, then the Perseus Cluster might be revealing cracks in that cosmic scaffolding. Simulations predict dark matter should clump together in predictable ways, dense knots near galaxy cores, tapering into wispy filaments at the edges. But when astronomers map Perseus using gravitational lensing and galaxy motions, the distribution looks patchy. Some regions show dark matter piled up like snowdrifts against a galactic fence, while others stretch nearly empty like voids punched through the fabric of space itself. This isn't just a minor mismatch between theory and observation. It's a full-blown crisis for our understanding of how the universe structures itself on the grandest scales. Take the cluster's northwestern quadrant, where gravitational lensing suggests a dark matter overdensity 3 times thicker than simulations projected. This massive clump bends light from background galaxies into arcs and rings, yet curiously, it hosts fewer visible galaxies than expected. Normally, dark matter and galaxies go hand in hand, their gravity mutually pulling them together. So why would dark matter pool here without a proportional gathering of stars? One provocative explanation involves primordial quantum fluctuations, tiny wrinkles in spacetime from the universe's first moments that might have seeded these uneven clumps before normal matter even existed. If true, we could be glimpsing fossil imprints from the dawn of time, preserved in dark matter's shadowy embrace. Then there's the opposite problem, baffling gaps. Near the cluster's core, where dark matter should be densest, observations reveal a donut-like hole, a region spanning thousands of light-years with shockingly low dark matter density. It's as if someone scooped out the cosmic equivalent of an apple's core, leaving behind a gravitational vacuum. Some theorists speculate this could be evidence of dark matter interacting with itself through unknown forces, scattering particles like billiard balls during ancient collisions. Others propose these gaps are the graveyards of dark galaxies, primordial clumps of dark matter that never attracted enough gas to form stars, then evaporated over eons under the cluster's relentless tides. The implications ripple far beyond Perseus. If dark matter clumps differently than our models predict, it could mean we've misunderstood its fundamental nature. Maybe dark matter isn't the simple, slow-moving particle we've assumed, but a more complex entity, perhaps a mix of warm and cold varieties, or even a fluid-like substance that flows and separates under extreme conditions. Alternative theories like modified gravity get a second wind from these discrepancies, though they struggle to explain all the data. Every unexplained clump or void forces us to question whether dark matter plays by the rules we've written, or if we've been missing a whole chapter of its behavior. What makes this mystery so electrifying is its double edge. Solve it, and we might finally crack dark matter's identity, unlocking one of cosmology's grandest puzzles. Fail, and we could face a paradigm shift, realizing the universe's hidden architecture follows blueprints we've yet to decipher. For now, Perseus keeps its secrets, its uneven dark matter map a tantalizing trail of breadcrumbs leading either to revelation or revolution. And that's the beauty of cosmic detective work. Sometimes the most revealing clues aren't what you find, but where the pieces refuse to fit. The Perseus Cluster's outer edges are supposed to be the calm after the storm, a place where the frenetic energy of the core gives way to cooler, more predictable conditions. But the universe loves a good plot twist. Observations reveal these outskirts aren't just warm, they're blistering, reaching temperatures that deflate our best theoretical models like a punctured balloon. According to standard cosmology, as gas falls into a cluster from the surrounding cosmic web, it should hit an accretion shock at the boundary, a cosmic speed bump where the infalling material slams into the cluster's atmosphere, heating up in predictable ways. Except in Perseus, the thermometer reads scorching hot well beyond where those shocks should fade, as if someone left a cosmic iron burning in the void. So what's cranking up the heat? One leading suspect is unresolved mergers, galactic pile-ups we haven't yet spotted. When smaller galaxy groups slam into the cluster at millions of miles per hour, they can inject energy like a splash of gasoline on a fire. These collisions don't just heat the gas directly, they send shockwaves rippling outward, stirring the outskirts like a spoon in a boiling pot. The catch: Perseus's outer regions show smooth, undisturbed gas patterns, lacking the turbulence or density spikes typical of recent mergers. It's like finding a scalding stovetop with no visible flame underneath. That's led researchers to wilder ideas, like cosmic rays acting as invisible agitators, charged particles accelerated by supernova or black hole jets might be zipping through the cluster's fringes, depositing energy as they collide with gas atoms. Think of it as microwaving the outer layers from within, where the heat source is everywhere and nowhere at once. Some models suggest these particles could transfer energy so efficiently they'd explain the temperature mismatch without leaving obvious fingerprints. But the most radical theory points to non-thermal processes, exotic physics we've yet to account for. Magnetic reconnection events where tangled field lines snap and release energy might be sparking silent flares in the gas. Or perhaps dark matter, if it interacts even slightly with normal matter, is subtly warming the outskirts through friction, like an invisible hand rubbing against the fabric of space itself. What makes this mystery so critical is its universal implications. If clusters like Perseus consistently run hotter than expected, it could mean our models of cosmic structure formation are missing a key ingredient, something that pumps energy into these systems long after they should have cooled. Maybe accretion shocks aren't the only game in town, or maybe the universe has a hidden furnace we've yet to discover. Either way, Perseus's overheated edges are more than a curiosity. They're a thermal enigma burning a hole in our understanding of how the cosmos cooks its largest structures. Among the Perseus Cluster's countless galaxies, a peculiar cosmic chorus has caught astronomers' attention: radio jets from multiple supermassive black holes, all pointing in eerily similar directions. These aren't mere coincidences. These jets stretch for thousands of light years, yet they align with precision that defies random chance. It's as if invisible cosmic conductors have orchestrated these eruptions to face the same way, a phenomenon that shouldn't happen without some unseen hand guiding them. The mystery begins with the jets themselves. When supermassive black holes feed on surrounding gas, they often launch twin beams of charged particles at nearly light speed, visible in radio wavelengths. Normally, these jets shoot out in whatever direction the black hole's spin axis points, an orientation thought to be random across different galaxies. But in Perseus, a significant fraction of these jets share a common alignment, like compass needles swayed by some massive, hidden force. One compelling explanation points to the cluster's magnetic fields. If Perseus is threaded with large-scale magnetic structures, invisible filaments stretching across millions of light years, they could act like cosmic railroad tracks, channeling the jets along preferred directions. Think of it like iron filings aligning around a magnet, except on a scale so vast it bends the very fabric of space. Observations from radio telescopes reveal faint, galaxy-spanning magnetic fields in Perseus, but whether they're strong enough to steer these jets remains hotly debated. Simulations suggest that over billions of years, even weak fields could nudge gas flows during galaxy formation, indirectly setting black hole spins and thus jet directions into alignment. Then there's the cluster's turbulent past. Perseus didn't assemble peacefully. It grew through violent mergers with smaller galaxy groups slamming into its core like comets hitting a planet. These collisions could have stirred the cluster's gas into vast, coherent flows, dragging black hole accretion disks and their jets into alignment like twigs caught in a river's current. Some astronomers compare it to a cosmic game of tug-of-war, where the cluster's gravitational tides gradually torque galaxies until their black holes spin in sync. Supporting this, the aligned jets tend to trace the cluster's large-scale filamentary structure, hinting at a shared history of motion. But the plot thickens when you consider outliers. A few jets stubbornly refuse to align, pointing in directions that clash with their neighbors. Are these rebels evidence of more recent arrivals, not yet synchronized with the cluster's flow? Or do they undermine the alignment theory entirely? The answer might lie in timing. If the process takes billions of years, perhaps we're witnessing snapshots of different evolutionary stages. What makes this enigma so tantalizing is its potential to reveal hidden forces shaping the universe. If magnetic fields or ancient flows can orchestrate black hole behavior on such scales, it suggests a level of cosmic order we've only begun to grasp. Worse yet, if no existing theory fully explains the alignment, we might be staring at evidence of something entirely new, a fundamental force or large-scale structure invisible to our current tools. For now, the jets remain a silent chorus, their synchronized directions a riddle written in radio waves, waiting for us to decode the conductor's baton. At the heart of several Perseus Cluster galaxies, supermassive black holes aren't just feeding their flickering like cosmic candle flames, their brightness surging and fading over timescales as short as days. These aren't the predictable pulses of steady accretion. They're erratic, almost nervous fluctuations from active galactic nuclei, or AN, that defy our models of how matter falls into these gravitational monsters. Imagine a strobe light in a thunderstorm flashing without rhythm. That's the level of unpredictability astronomers are grappling with. The first clue lies in the accretion disks, those whirling maelstroms of gas and dust spiraling into the black holes. Normally, these disks should glow steadily as friction heats them to millions of degrees, but in Perseus, something destabilizes the flow. One leading theory suggests magnetic instabilities are at work, with fields twisting until they snap like rubber bands, triggering sudden bursts of energy. Supporting this, X-ray observations reveal hotspots in the disks that flare and vanish faster than standard physics allows, as if the black hole's dinner plate keeps cracking under the strain. Then there's the jet precession puzzle. Some flickering AGN show telltale signs that their particle jets, normally steady as lighthouse beams, are wobbling wildly, their orientations changing over weeks. This could happen if the black hole's spin axis gets knocked askew, perhaps by a recent galactic collision or a clump of infalling matter striking the disk at a rogue angle. As the jet sweeps across our line of sight, its brightness would swing dramatically like a flashlight beam panning past your eyes. But the wildest possibility involves cosmic sabotage, thick clouds of gas drifting between us and the AGN, blotting out their light intermittently. These wouldn't be ordinary clouds, they'd need to be dense, fast-moving structures, possibly debris from shredded stars or turbulent eddies in the accretion flow itself. Some observations catch the AGN's light reddening just before dimming, a fingerprint of dust scattering shorter wavelengths. Yet the speed of these changes suggests the clouds are improbably close to the black hole, enduring gravitational tides that should tear them apart. Unless, of course, they're held together by forces we don't yet understand, magnetic fields or even dark matter's invisible grip. What makes this flickering so revolutionary isn't just the technical puzzle. It's a window into black hole feeding habits on the tiniest scales. Most AGN variability happens over years, but Perseus' rapid-fire changes imply we're witnessing processes near the event horizon itself, where time and space warp beyond recognition. If instabilities rule here, it might explain why some black holes seem to flicker on and off across cosmic history, not because they lack fuel, but because their dining experience is inherently chaotic. The implications ripple outward. If accretion disks are more turbulent than we thought, our estimates of black hole growth and energy output might need recalibrating. And if obscuring clouds really do survive so close to the abyss, they could rewrite our playbook for how matter behaves under extreme gravity. For now, though, the flickering continues, each erratic pulse a Morse code from the edge of physics, daring us to decode its secrets. Tucked among the Perseus Cluster's vibrant galaxies, there's a population of cosmic zombies galaxies that burned bright with young stars long ago but now drift as lifeless husks. Their star-forming fuel exhausted billions of years earlier than expected. These red and dead galaxies glow a dull crimson in telescope images, their light dominated by ancient red stars with no blue spark of newborn stellar nurseries. They shouldn't exist in such abundance, at least not according to our models of how galaxies age. In most environments, galaxies this massive would still be churning out stars today. But Perseus, it seems, has a knack for killing galaxies young, and the methods are chillingly efficient. The first clue to this galactic murder mystery lies in the cluster's extreme environment. Packed with galaxies and superheated gas, Perseus is a gravitational pressure cooker where close encounters and violent mergers are inevitable. When a galaxy falls into this maelstrom, it doesn't just drift peacefully, it's bombarded from all sides. Ram pressure, the drag force from moving through the cluster's thin but searing plasma, acts like a cosmic blowtorch, stripping away the cold hydrogen gas needed to form stars. Think of it as a hurricane ripping the shingles off a roof, leaving the structure intact but unable to shelter new growth. Observations from radio telescopes reveal trails of gas streaming behind these galaxies like cosmic tears, evidence of this brutal stripping in action. Yet ram pressure alone can't explain the scale of the carnage. Some red galaxies sit surprisingly far from the cluster's core, where the gas is thinner and stripping should be less dramatic. This suggests a second killer at work, strangulation. As galaxies orbit the cluster, their outer reservoirs of gas, the fuel reserves for future star formation, get siphoned away by the cluster's collective gravity, a process called tidal stripping. Deprived of fresh material, these galaxies aren't just wounded, they're starved slowly, their stellar nurseries shutting down over a few 100 million years. It's the difference between a sudden amputation and a prolonged famine, both ending in the same grim fate. But here's where the plot twists. Some of these dead galaxies show signs of a much quicker demise, far too quick for stripping or starvation to explain. Their star formation didn't taper off, it slammed shut like a vault door. This points to a third, more violent mechanism, mergers. When two galaxies collide, the chaos can trigger a burst of star formation that burns through gas reserves in a frenzy, followed by a catastrophic shutdown as the remaining fuel is ejected or consumed by the resulting supermassive black hole. In Perseus, where galactic traffic jams are common, such crashes might have been the final nail in the coffin for many galaxies, their star-forming potential snuffed out in one dramatic event. The real puzzle, though, is why Perseus quenching methods are so ruthlessly effective compared to other clusters. One theory suggests the cluster's unique history, particularly its early formation, gave it a head start in galactic demolition. While younger clusters are still assembling, Perseus may have reached critical density billions of years ago, allowing its environmental killers to operate uninterrupted for eons. Another idea points to the cluster's magnetic fields, which could amplify stripping by locking gas into place, making it easier to tear away. And then there's the dark matter factor. If Perseus' dark matter halo is unusually concentrated, its gravitational grip might be choking galaxies faster than we've seen elsewhere. What makes these dead galaxies so unsettling isn't just their existence, it's what they reveal about the universe's relentless brutality. In most environments, galaxies die of old age. In Perseus, they're murdered in their prime, and if this cluster's methods are more common than we thought, it could rewrite our understanding of galactic life cycles, proving that sometimes the universe doesn't just let things fade away, it actively silences them. The red galaxies of Perseus stand as tombstones in a cosmic graveyard, their crimson glow a warning. In the densest corners of the cosmos, even giants can fall. Deep in the Perseus Cluster's gravitational grip, background galaxies billions of light-years farther away should appear stretched into smooth arcs, their light bent predictably by the cluster's immense mass. Yet something's off. Some of these distorted galaxies show kinks and warps that don't align with Perseus' expected gravitational blueprint, as if invisible fingers are tweaking the cosmic lens. These anomalies aren't random noise, they're systematic discrepancies that could expose either hidden pockets of mass or cracks in our understanding of gravity itself. The first red flag emerged when astronomers compared Hubble's razor-sharp images of lensed galaxies with detailed mass maps of the cluster. Based on the visible matter stars, gas, and the inferred dark matter distribution, the lensing distortions should follow specific symmetrical patterns. Instead, certain arcs bend too sharply at the edges, while others ripple with unexpected substructure, like a funhouse mirror with localized imperfections. One particularly striking example shows a background spiral galaxy stretched into an arc that suddenly zigzags near its midpoint, as if an unseen mass concentration is warping spacetime more intensely in that spot. This raises two electrifying possibilities. First, Perseus might be littered with dark matter clumps too compact and dense for current telescopes to detect directly cosmic icebergs where 90% of the mass lurks invisibly below the surface. These could be the remnants of ancient subhalos, dense knots of dark matter that survived galactic mergers intact. Simulations predict such substructures should exist, but finding them requires indirect methods like these lensing anomalies. If confirmed, they'd reveal dark matter's clumpiness on small scales, a key test for theories about its nature. The second possibility is even more radical. Einstein's general relativity might need tweaking at galaxy cluster scales. Modified gravity theories, like modified Newtonian dynamics, propose that gravity behaves differently in extreme low acceleration environments, precisely the conditions found in a cluster's outskirts. While struggles to explain all cosmic observations, these lensing anomalies align suspiciously well with regions where its predictions diverge from standard models. Some researchers suggest a hybrid approach. Perhaps certain dark matter particles interact weakly with themselves, subtly altering gravity's grip in ways that mimic modifications to relativity. The plot thickens when you consider timing. Some anomalous lensing features appear preferentially along the cluster's filamentary structures, those vast, web-like tendrils of galaxies and gas connecting Perseus to neighboring clusters. If these filaments contain more mass than assumed, or if their dark matter has unique properties, it could explain why lensing distortions spike in specific directions. Alternatively, the anomalies might trace the ghostly wakes of galaxies that plunged through Perseus long ago, their dark matter halos stretched into invisible streams that still bend light like submerged logs diverting a river's flow. What makes these gravitational quirks so pivotal is their dual promise. They could either uncover hidden chapters in dark matter's biography or force us to rewrite gravity's rulebook. For now, each warped arc and kinked galaxy is a cipher waiting to be decoded, a reminder that even in the silent tug of gravity, the universe leaves room for surprise. The Perseus Cluster isn't just bending light and warping galaxies, it's also a cosmic particle accelerator, bombarding space with mysterious high-energy cosmic rays that shouldn't exist. These aren't your garden-variety space particles. They're ultra-high-energy protons and atomic nuclei screaming through the void with energies millions of times greater than anything our most powerful colliders can produce. And when astronomers trace their paths backward, many seem to originate from Perseus' chaotic core, despite no obvious source capable of launching them. It's like finding bullets fired from a gun that no one can see, or worse, a gun that shouldn't even exist. At the heart of the puzzle is a glaring mismatch between theory and observation. Cosmic rays are usually born in extreme environments, supernova shockwaves, colliding neutron stars, or the jets of active black holes. But in Perseus, the numbers don't add up. The detected cosmic ray flux is 10 times higher than what known astrophysical engines should produce, and their energy spectrum peaks in ways that defy conventional acceleration models. Some particles clock in at over 10 to the 18th electron volts, energy so absurd they border on the mythical. So where does the cluster hide its secret launcher? One electrifying possibility involves dark matter annihilation. If dark matter particles occasionally collide and annihilate in Perseus' dense core, the resulting energy could spawn cascades of cosmic rays. Simulations show certain theoretical particles, like weakly interacting massive particles or sterile neutrinos, might decay into standard particles, producing exactly the sort of excess we observe. The fact that the signal seems concentrated near the cluster's gravitational center, where dark matter should be densest, adds weight to this idea. But there's a competing theory just as wild. Perseus might be hosting a natural supercollider far deadlier than anything on Earth. When galaxies in the cluster collide, their magnetic fields twist into monstrous knots, creating shock fronts that could slingshot particles to unfathomable speeds. Picture a pinball machine the size of a galaxy, where protons ricochet off magnetic barriers until they're hurled into space like subatomic cannonballs. Some researchers argue that turbulence in the cluster's superheated plasma could amplify this process, turning Perseus into a particle accelerator of cosmic proportions. Yet the plot thickens when you examine the particles themselves. The cosmic ray excess isn't uniform, it's lopsided, with more rays coming from the cluster's northwestern quadrant, the same region where gravitational lensing reveals an unexplained dark matter overdensity. Could this asymmetry point to a localized dark matter hotspot? Or is something else lurking there, like a hidden black hole spewing jets we can't detect? The data remains frustratingly silent. What makes this cosmic ray enigma so pivotal is how it bridges particle physics and cosmology. If dark matter's the culprit, studying these particles could reveal its identity after decades of speculation. If it's an unknown astrophysical beast, we might need to rewrite the rules of particle acceleration. Either way, Perseus isn't just challenging our models, it's hurling subatomic riddles at us, one ultra-high-energy particle at a time. And in their silent impacts, there's a lesson. Sometimes the universe's most profound secrets arrive not as light or gravity, but as bullets from the dark. From missing dark matter to ghostly radio halos, rogue black holes to flickering quasars, the Perseus Cluster has spent this entire video throwing cosmic curveballs at everything we thought we knew. Each of these 25 unexplained phenomena isn't just a gap in our knowledge, it's a crack in the foundation of modern astrophysics. Take those eerie cold fronts slicing through million-degree gas, defying thermodynamics like ice cubes in a furnace. Or the way galaxies align their jets like obedient soldiers, hinting at unseen forces orchestrating chaos. Even the cluster's very structure rebels, with dark matter clumping where it shouldn't and vanishing where it must. Every mystery we've explored whispers the same unsettling truth. The universe operates with a playbook we've only glimpsed. What makes these puzzles so electrifying isn't just their individuality, it's how they intertwine. The missing dwarf galaxies might connect to those unexplained gamma-ray excesses. The turbulent gas that refuses to cool could be tangled up with the black hole's rhythmic eruptions. And those rogue cosmic rays, they might be screaming clues about dark matter's true nature. Together, they paint Perseus not as a static cosmic museum, but as a living laboratory where the laws of physics stretch, warp, and occasionally snap under pressure. This is why galaxy clusters terrify and thrill scientists in equal measure. They're the universe's ultimate stress tests, places where gravity, magnetism, and particle physics collide at scales we can barely simulate. Every anomaly forces us to ask, are we missing a piece of the puzzle, or is the puzzle itself fundamentally different than we imagined? When a single cluster can simultaneously break our models of dark matter, gas dynamics, and black hole behavior, it's either a cosmic conspiracy or a signpost to deeper truths. So where do we go from here? That's where you come in. Space isn't just for astronomers, it's for anyone who's ever looked up and wondered. Which of Perseus' secrets fascinates you most? Is it the wayward black hole barreling through the void, or the star clusters thriving against impossible odds? Drop your pick in the comments and let's geek out together over the universe's weirdest neighborhood. And if you're hungry for more deep dives into space's unsolved mysteries, hit subscribe, because the cosmos has plenty more riddles where these came from. After all, the greatest lesson Perseus teaches isn't about any single phenomenon. It's that the universe will always be stranger, messier, and more magnificent than our theories dare to predict. And honestly, that's what makes exploration so